McLeod. Okay, thank you. Thank you. Very loud. So this was your little bonus opportunity, was the review. So using the sample data below, answer the following questions. So the first part, calculate the mean and the mid-range. So the mean, since we have a sample, is X bar. You find it by just adding all the data values and dividing by the total number. So it's 6 plus 12 plus 9 plus 8 plus 11 plus 7, and then divide that by 1, 2, 3, 4, 5, 6. So if you do that, what did y'all get? Yeah, 8.83 to 2 decimal places. So what about the mid-range? How do you find that? Yeah, add the min and the max, divide by 2. So the minimum value is 6, the max is 12. So 6 plus 12 over 2, that's 18 over 2, or 9. So some people miss this second part, so you could literally plug it in your calculator to do it. I can't remember if I did that or if I did it by hand, but notice that you're given the sample data, so you need the sample standard deviation, the sample variance. So the sample variance S squared, if you use a formula, is the sum of the xi, so each data value minus the sample mean, so squared divided by n minus 1. So what would that look like? We would have 6 minus 8.83 squared plus 12 minus 8.83 squared, all the way up until 7 minus 8.83 squared, and then divide by n minus 1. So n in this case is 6, so you divide by 5. And someone who thinks they got it right, what'd you get? Yeah, 5.37 or 5.4, either one's fine. So then you have the variance. So what do you do to find the standard deviation? Yep, take the square root. So then S is just the square root of 5.4, which is roughly, I put 2.32. So some of you missed that part. Some of you gave me the population variance and population standard deviation. So the next part, find the percentile rank of 11. So some of you gave me the wrong one here. So the first thing you have to do is put them in order. So you have 6, 7, 8, 9. Holy cow, that was loud. You all good? Oh, loud. It happens. Holy cow, there's a lot of people online. Okay, so then to find the percentile rank of 11. How do you find that? The number of values less than 11 plus 0.5 divided by the total number of values n. So some of you put n as 10. That was the one we did in class, which was wrong. So this one was 6. So then the number of values less than 11, we have 1, 2, 3, 4, 6, 7, 8, 9. So that would be 4 plus 0.5 divided by 6 times 100. And what do you get? No. 75. 4.5 divided by 6. So 4.5 divided by 6, that's 3/4. Multiply it by 100%. You get 75. So that's how you did that one. So some of you even wrote that this implies that 11 is in the 75th percentile, which is also correct. Everyone okay up to there? Awesome. So then the next one, what is the value corresponding to the 30th percentile? So to do this, use the C equals NP over 100. So N is 6, P is what? 30. Divide that by 100, you get what? 1.8. So we said if C is a decimal, round up to the next whole number. So that means we're going to take C as 2. So then we go to the second number in the ordered list above. And if you do that, you get 7. So that implies 7 is in the 30th percentile. So, and then the final one, which is where most of you got stumped. If you use your calculator, you wouldn't have got stumped, but if you use the formula I gave you, it kind of stumps you. So I'm just going to show you what it is. So draw the box plot, be sure to check for outliers. So what I did was I first found the 5-number summary. So you have an even number of data values. So the median, find that first by taking the average of the two most middle. And if you do that, you average 8 and 9. And the average of 8 and 9 is what? 8.5. So that means that we're actually dividing the data set into those two groups there. So these are the data values below the median. So when we take the median of those, you get 7. Some of you added 6 and 7. So, and then similarly, some of you added 11 and 12. So does everyone understand why that is, or kind of why the answer is what it is? So if you do that, you get that the first quartile is 7, third quartile is 11, and then you can check using the IQR rule. So here we have Q3 is 11, Q1 is 7, so the IQR is 4. So then you can check to see if there are any outliers using the two rules we had. What was the most bonus points? 5? It was 3. So whenever we take Q1, so that's 7 minus 1.5 times the IQR, which is 4. So that's 7 minus 6, which is 1. So are there any data values less than 1? No, the smallest is 6. So then using the same idea, we do it for the upper end. Q3 is 11, and then we add 1.5 times the IQR. So it's 11 plus 6, or 17. Are there any data values greater than 17? No. So there are no outliers. So that means that 6 and 12 are the actual min and max. So then you can draw the box plot. And what can you say about its distribution? I don't think I asked for it. Slightly right skewed. What up? Okay. So why was it 7 and 11 again? Okay. So whenever we're talking about Q1 and Q3, so Q1 is the median of the data values that fall below the median. So in this case, our median was 8.5. So we need to look at the values that fall below 8.5 and find the median of those. So if I do that, 6, 7, and 8 are all less than 8.5. So then I need to look at the median of these 3 values. And if I do that, I get 7. Does that make sense, Bailey? Okay, and you can do the same thing for the upper ones as well. So if you would have plugged it in your calculator, it would have gave you those as well. So is everyone okay with that? Cool. So if yours isn't graded yet, I will do it later today, sometime, whenever I get to it. So that is all for chapter 3. So now on to the hardest chapter for the first exam, chapter 4. It's not that hard. Although some of your homework questions are kind of tricky. So I'll go over those. Okay, so I'm trying to figure out, when is your exam scheduled? No, it's not. It's the yeah, it's not next Tuesday, but the Tuesday after. Yeah. Okay, cool. So I'm trying to figure out how many questions will be on it. Heck if I know. Not too many, but enough so you can complete. What? No. No, not even close.
Like 20?
Yeah, something like that. I'll post an old one for you. I don't know what I'm going to put on it yet. I haven't really looked at it. So there'll be 2 forms for the exam. I'll have 2 different ones since there's so many people in here. I don't want to catch someone cheating. I don't think you want me to tell you to withdraw from the class. Yeah, that's never fun. You always feel bad. But stuff happens. So chapter 4 is all about probability. So you've heard of that, right? So like when you toss a coin, what's the probability of getting a head or a tail? Half and half for each because one's equally likely. Exam is paper, right? Yes, it is. And you're allowed 1 sheet of notes, front and back, just the standard 8.5 by 11. Yeah. No. If I gave you an exam on Alex, it would be a lot harder than what I write. Alex uses some quite large questions, some quite large numbers.
So on the exam, we use the Excel for all our students?
No, it's not gonna be that hard.
It's not gonna be like.
Yeah, it's everything you can do on your calculator. Yeah. So you won't get anything quite big. So I usually make them relatively doable. Okay, so if the chapter 4 is all about probability, then obviously we need to talk about what is probability first. So a general definition it is the chance of some event occurring. So you could talk about what's the probability of you winning the lottery? Not good. I wish it was. So you could also talk about the probability of passing your first exam. Hopefully that's high. We'll see. So the first thing we're going to define is what is called a probability experiment. It is a chance process that leads to well-defined results, which we call outcomes. Probability. So now that we just said that it produces well-defined results called outcomes, what are outcomes? So an outcome is a result of a single trial of a probability experiment. I don't know how some professors like writing so much of a probability experiment. So what in the world does that mean? So let's look at an example to kind of illustrate what that is. So it says tossing a coin and getting a head. So what is the probability experiment and what is the outcome? So the probability experiment, by definition, is a chance process that leads to well-defined results called outcomes. So in this case, what are we doing to get some result? Tossing a coin. So tossing a coin is the probability experiment. And then what is the outcome it's talking about? Getting ahead. So it's just getting ahead. So now, whenever we toss a coin, there are two possibilities. You get heads or tails, and these two make up what is called the sample space. So the sample space, which we denote S, is the set of all possible outcomes of a probability experiment. So where in the world did they put the blue marker? Why are they making me walk so much? Oh, dang it. They took the good expo one. Them thieves. Okay, so I'm going to turn this camera around so they can see it. I'm going to do it on the board. There, got it. So the first one, the experiment says tossing a coin. So if you toss a coin once, you get two outcomes, either head or tails. So then the sample space S is just the set containing heads and tails. So what if I roll a dice or a six-sided die? What are the possible outcomes? Yeah, 1 through 6. It could land on 1, 2, 3, 4, 5, or 6. So then for the second one, S is just the set of numbers 1, 2, 3, 4, 5, and 6. Is everyone okay with that? So then the last one says tossing 2 coins. So if I toss 2 coins, you get a head and a tail. The first toss, then you can do the same thing, get a head or a tail, then a head or a tail. So then to find what are the outcomes, you just trace along these branches. So you have a head and a head. So S is a head and a head and a tail and a head, and a tail and a tail. Everyone understand how I did that? Just tracing along these branches to get those 4 outcomes. So I don't know if we'll put this on the exam or not, but if you toss a coin in times, how many outcomes are in the sample space S? So if I toss it once, there's 2. If I toss it 2, there's 4. What do you notice between those 2? Yeah, it doubles. So each time I go up 1 step, it doubles. So I have 2 to the first for this first one, 2 to the second for this one. So if I do this n times, how many outcomes should be in the sample space? 2 to the n. That makes sense? Because you're just tossing a coin n times, and each time you have 2 possibilities. Okay, so that is all for the first page. Okay. Okay. Now let me turn it back around to there. So if the sample space contains no outcomes, we call this what is known as the empty set. So what does that look like? So S is just the set with nothing in it. And you can denote that by a 0 and then draw a vertical line through it. Before the last two blanks, what was the last two blanks before the examples? It was, yes, sample space. Oh, I should probably show you what I set up here. So in the last one, it says, what does it say? If the sample space contains no outcomes, then we call this the empty set. Basically, it's a set with no elements. And this is what it looks like. So it's just curly brackets with nothing inside. And then we're going to denote the empty set with that. It's called the null set. X. Okay. So clearly the sample spaces we found by observation and the reasoning and the previous examples, but when the sample space becomes large, then it becomes difficult to actually visualize it. So we create what is called a tree diagram. And why is it called a tree diagram? Because it looks like a tree. Turn it that way, you get a Christmas tree. So, let's see if I can get that right. Ta-da. So, everyone okay up to there? Everyone online, have I confused you yet? Awesome. So let's look at this example. Use a tree diagram to find the sample space of 3 consecutive coin tosses. So let me turn this back over here so they can see it online too. Okay, so this example, we did 2 coin tosses. So all you do is do another one. So for each of these outcomes right here, you have 2 more, a head and a tail, a head and a tail, a head and a tail, and a head and a tail. Okay. And then if you want to write the sample space, then you again trace along the branches. So you have head, head, head. Head, head, tail. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. And then tail, tail, tail. So does it matter which order these go in? The answer is yes. So, and how many outcomes are in this? 1, 2, 3, 4, 5, 6, 7, 8. 2 to the third is what? 8. So that's how you'd use a tree diagram to do 3 consecutive coin tosses. So you could also do something similar for true and false questions. I can't remember if your homework does that or not, but here you just have true, here you have false, and it does the same thing. So it'd be, what is the total what's the sample space for like three true false questions, and just replace these H's with T's, or you can just replace them with F's. and you get the same kind of idea. Everyone cool up there? So then the next thing we'll talk about is what is called an event. So an event E consists of a set of outcomes of a probability experiment. So, and if this event E just contains one outcome, we call it what is known as a simple event. And if it contains more than one outcome, what do you think it is? What's up? Close. Yeah, the first four letters, right? Yeah, compound. Compound event. So you should be able to look at the event E, so the outcomes that are in it, and then determine whether it is a simple event or a compound event. So that is just based off how many things are in there, one or more than one. So then looking at that example where it says rolling a die, event 1 is rolling a 2. So let's let E be this. So, and if we roll a 2, what's the only outcome in our event E? The number 2. So that would make a bar event. And since there's only one outcome in it, then what is it? Simple. So I guess I can introduce this before it actually comes up later. So does anyone heard what the complement is? So the complement is the opposite. So the opposite of rolling a 2 would be rolling a what? Anything but a 2. So a 1, 3, 4, 5, and 6. So that E bar denotes the complement. We'll talk about that later. But if I bring it up earlier, it may make sense. Oh my Lord, there's something there. So for that first one, E bar was 1. Nope, not 2. 2 was actually in there. 1, 3, 4, 5, and 6. How many outcomes are in E bar? 5. How many outcomes are in E? 1. How many sides are on a die? 5 plus 1 is 6. Woo, math. So event 2, rolling an even number. So what does that consist of? So the numbers on a die that are even. So E2 is so rolling an even number. So 2, 4, and 6. So there's 3 outcomes. So what is that? A compound event. So then what is the complement of E2? Yeah, 1, 3, 5, rolling an odd number. So there's 3 outcomes here, 3 outcomes here. 3 plus 3 is still 6. Everyone following along up to there? Awesome. There, I'll turn the camera back around. Now let's keep it over here. So classical probability is the first thing we'll talk about. So there's 3 different types. There's empirical, classical, and the other one will come to my mind later. I can remember it. So the first one we'll talk about is what is known as classical. So classical probability uses sample spaces to determine the probability that an event will happen. This means that you do not actually have to perform the experiment. And why? So I'll just tell you the answer. Because in classical probability, so prob is my shorthand for probability. In classical probability, every outcome is assumed to be equally likely So what does that mean? Yeah, they have the same chance of happening for all of them. So then looking at that first example, it says rolling a die. So we have 6 numbers. And if it's a fair die, then each of them should have probability of what? 1/6. So then I would have 1, 2, 3, 4, 5, and 6. And their corresponding probabilities below them. So it would be 1/6, 1/6, 1/6, 1/6, and 1/6, and another 1/6. So if I add up all of these probabilities, what do I get? So 1/6 times 6 is 6/6 or 1. Everyone see that? Cool. So then we can come up with what is known as the classical probability formula. So let's let that go bye-bye. So the classical probability formula is equal to NE over NS, where NE is the number of outcomes in the event E, and what do you think NS is? Is the number of outcomes in the sample space S. So it's just the definition your book gives. So what else does it say? Oh, I thought I said that earlier. Can you also hear me online? Yep, you can. Cool. So that is the formula we're going to use to find the classical probabilities. So let's look at an example. So the first one says, in a 3-question true or false quiz, find the probability that exactly 2 questions are false. So what do you think the first step you need to do is? Yeah, true diagram. So it's basically the same thing as what we did for a coin toss. You have true, false, true, false. Probably need to make that. Everyone okay with how you did that? So you start with, you get one true and one false. And then for each of those, you have another true and false. And for each of those, you have another true and false. So again, just like we had with a coin toss, you can have two of the n possibilities for n true and false questions. So in this case, it's 3. So 2 to the third is 8. And actually, if you count the numbers in this last column, it'll also be the same. 1, 2, 3, 4, 5, 6, 7, 8. So now to find the sample space S. So that would be just the set of all possible outcomes from 3 true and false questions. So all you do is read along the branches. So you have true, 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 false, true, false, true, true, false, false. So then false, true, true. Oops. So false, true, true, false, true, false. False, false, true. And false, false, false. And that is the sample space S. Everyone agree with me on that? Okay. So then the second step, we want to define the event. So the event E is when we have exactly 2 questions are false. So what we're going to do in this sample space is look for where there's exactly 2 falses. So if you do that, no, 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 yes, no, yes, yes. So then the event E, the outcomes in it consist of these 3 outcomes here where we have 2 falses. So it'd be true, false, 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 true, false, and false, false, true. Everyone understand that? So would the event E change if I said at least 2 questions are false? Yes. So what other outcome would be included? Yep, false, false, false. Correct. This one. So the next step, find the probability of the event E. So just use this formula here. So the probability of some event E is equal to the number of outcomes in the event E divided by the total number of outcomes in the sample space S. So then if I want to find the probability of E, I have how many outcomes in E? 1, 2, 3. And how many outcomes in S? 1, 2, 3, 4, 5, 6, 7, 8. So my probability is 3/8. So if you want to put that in decimal form, that's 0.375. Okay. So if that is our event E, then similarly, we can define the complement of that. And that would be where we don't have exactly two questions false. And that would be which outcomes up there. What do you think? Yeah, ones that are underlined. So then if we are looking at E bar, the complement, then those would be true, 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 false, true, false, true, false, true, true, and false, false, false. How many outcomes are in E bar, the complement? 5. So then the probability of E bar is what? So there's 5 outcomes in E bar divided by 8 outcomes in S. If I add the probability of E and E bar, what do I get? 1. And should I always get 1? Yes, so either an event's going to happen or it's not. And the probability of those two added together should give me 1. So that implies the probability of E plus the probability of E bar is 1. Know that formula. It will guaranteed pop on the first exam and probably your final. The event was, yes, the event was compound in both cases. So E was compound and E bar, the complement, were compound as well. Oopsies. Everyone following? Awesome. So then the next thing we'll talk about is some probability rules. So the probability of any event E is a number between 0 and 1. So that's kind of obvious. So you can't have more than 100% chance of something happening, and you can't have less than a 0% chance of something happening. So obviously it needs to be between 0 and 1. Can it include 0 and 1? Yes, it can. So the sum of all the probabilities of all the outcomes in a sample space is 1. So what does that mean? Yeah, so if I just add all the probabilities, how should I describe this? So how many outcomes are in S? 8. So then how many outcomes are, it's just S over S, which is 1. So that's why. So if an event E cannot occur, then what do you think its probability should be? So if E cannot occur, then obviously its probability should be 0. E can't occur implies the probability of E equals 0. And if E is certain to happen, then what should its probability be? Yep, 1. So if E is certain, that implies the probability of E is 1. Everyone following up to there? So it's not too bad so far, is it? It'll get worse. So, and the next thing we'll talk about is what I've been talking about since actually the beginning, complementary events. So I guess I'll just write the definition up here, what it says in your notes. So the complement of some event. Let's just start here. The complement of some event E, which we denote E with a bar on the top, is the set of, how did I write it? All outcomes in the sample space S that are not included in the event E. So we already did this example 1. So if a single die is rolled, what is the probability of getting an even number? So in that case, E would be getting an even number. And there are 3 ways to do that. On a die, you have 2, 4, 6. So then the probability of E is the number of outcomes in E, which is 3, divided by the number of outcomes in S. So if I toss a coin, there are 6 possibilities. The probability is 1/2. So then what is the complement of getting an even number? Odd number, obviously. So then E bar is 1, 2, not 1, 2, 1, 3, and 5. And then the probability of that is the number of outcomes in it, 3, divided by the total number of outcomes in S, 6. And again, you get 1/2. What is 1/2 plus 1/2? Again, it's 1. So here, again, you see that the probability of E plus the probability of E complement is again 1, and it always will be. So then I said important, remember the following. I think I put that in there, didn't I? The rules for complementary probabilities. So they're all right there. So we came up with this one. So then similarly, we can find the probability of E by solving for it. Just take 1 minus the probability of E complement. Everyone see that? Subtract E complement from both sides, subtract the probability of E complement. You get this. Then to find the probability of E complement, what is it? Just manipulating this again, you have what? Yeah, 1 minus the probability of E. And those are 3 rules. They all come from this first one. So either something is going to happen or it's not. And if I add the 2 probabilities, it gives me 1. So example 2, in a survey, 25% of people said they preferred science as their favorite subject. What is the probability that a randomly selected person's favorite subject is not science? So what I said is let E be where science, SCIENCE, is the person's favorite subject. So then the probability of E is what? So it tells you in that first line, in a survey, 25% of people said they preferred science as their favorite subject. So the probability of E is 25% or 0.25. So then you can find the probability that science is not their favorite subject using this bottom one. So using the probability of E complement is 1 minus the probability of E. This implies the probability of E complement is 1 minus 0.25 to 0.75, which is also what? 75%. So the probability that science was your favorite subject was 25%. Probability that it's not is just 100% minus 25% or 75%. So then the next thing we'll talk about is what is known as empirical probability. So that's the second type of probability. Oh, I remember the third one. Classical, empirical, and subjective. So empirical probability relies on actual experience to determine the likelihood of outcomes. So in that case, not each outcome has the same probability of happening. So then what does that mean? In empirical probability, you actually have to conduct an experiment to find probabilities. So, and what did we do in chapter 2 at the very beginning? Anyone remember? So we did frequency distributions, so they come up here. So whenever we talked about relative frequency, whenever we talked about graphs, it was the probability that relative from one class to the whole entire sample, right? So it's the same idea here. So then we can come to this formula. So the empirical formula, or the formula for empirical probabilities, I say, is equal to the probability of some event E is equal to the frequency for that class. So the frequency of class divided by, what do you think? Just like how we had before in chapter 2, we took the frequency of one class divided by the total. You're gonna do the same thing here, the total frequency. So what time is it? 11:26. So let's see. What else? do I have to cover? I'm just trying to see what I'm trying to cover today. So let's look at this first example. Using the following frequency distribution, find the probability that a randomly selected student's test score is a B. So what is the frequency of B? 12. And what is the total frequency? You have 6 plus 12 is 18, plus 13, 31, plus 9, 40. So the total is 45. So then you have the probability of a B test score is equal to the frequency of B's over the total frequency. And we already said the frequency of B was 12. And the total was 45. So it says the very bottom of the page, where have we seen this before? And again, I just said it already. Relative frequency in chapter 2. So if you have the page, what is the probability that a person got an F on the test? Yeah, there's 5 people that got an F out of 45 students. Please don't get an F on the first exam. It's the easiest one. If you get an F on the first one, you'll probably get an F on the last 2. So let's look at the second example. So it says in a sample of 50 people, 21 had type O blood, 22 had type A, 5 had type B, 2 had type AB. Set up a frequency distribution. So what is it asking you to do? It's basically asking you to do what we did in chapter 2. So you have blood types on the left. So you have A, B, and O. And then to the right, you have the frequency. So how many people had type A blood? 22. How many had type B? 5. What about AB? You said 2. And O. Okay, so 21 plus 7. What the? Okay, that's right. Never mind. Brain went off for a second. So then if I add up these, I should get 50. That's 27. That's 23. 23 plus 27 is indeed 50. So this is the frequency distribution part here. So the first question says, find the probability that a person has type B blood. So just use the formula, the frequency of B over the total frequency. So we had 5 B's. Divided by a total frequency of 50, which is 0.10. So these next two are kind of tricky. So part B, find the probability that a person has type A or type B blood. Yeah, so you just take these two frequencies and add them together. So the probability of A or B is the probability of A plus the probability of B. That is 22 plus 5 over 50, or 27 over 50. The next one is a trick question. Find the probability that a person has type A and type B blood. Okay, someone got it right online. The probability is 0. So having type A and type B blood is different than having type AB blood. So you can't have type A and type B. So it's impossible. So therefore its probability is 0. Having A and B blood type is different than A B blood type. So you can't have type A and type B, so its probability is 0. Has anyone seen this symbol and this symbol? Okay, so the intersection is represented by that. It's pretty much an upside down U. And this is the intersection, or and. And then whenever we flip it upside down, it's like a U. And this is called the union. And it's 4. So the final question, find the probability that a person does not have type O blood. What's up? Yeah, you could do that, or you could look at the probability of type O and how many people have type O blood. 21. Take the probability of that, subtract it from 1. You get the same thing. So the probability of O complement, just using the complementary rule, is 1 minus the probability of O. And the probability of O is the frequency of O divided by the total. So it'd be 21 over 50. So it's 1 minus 21 over 50, or 29 over 50. So that's the answer to D. Everyone following up to there? Does anyone have any questions? Cool. So then let's move on to the final probability we talked about, which is called subjective probability. So I'm going to change it back to the document camera because it's kind of hard to draw on the board. So subjective probability uses basically an educated guess or an estimate. So an example, a meteorologist said there's a 30% chance of rain. So they said there was a good chance of snow yesterday, but we didn't get much. Or at least didn't whenever I lived. We don't get formulas here, just know definitions and examples. So the first one we'll look at is this. So suppose you roll a die twice. Here is the sample space. So here you could roll a 1 to a 6 on the first die, on the first roll, and then the second roll, you can roll a 1 through 6. So total, how many possible outcomes do you have? 6 times 6, or 36. So now it says find the probability of getting a sum of a 5 or a 6. So can you get a 5 and a 6 at the same time if you are summing 2 of them? No. So then, oops. So then I'll throw this in here earlier. It's in the next chat, in the next section. So if two events cannot occur at the same time, we call these anyone got a guess? Are we supposed to, oh, oops. There you go, now you can see it. I just wrote this. So if two events cannot occur at the same time, then we call these mutually exclusive. So, and then this will come into play whenever we're solving this. So if two events are mutually exclusive, then their probabilities do what? What do you think? So in general, if two events aren't mutually exclusive, the probability of A or B is the probability of A plus the probability of B. But if they can happen at the same time, then I counted something twice. So I need to subtract off the probability of A and B. So if two events are mutually exclusive, then the probability of A and B is 0. And this goes away. So I just have to add the probability of A and B. So why did I say that? So the first one says find the probability of getting a sum of 5 or a 6. So these two can't occur at the same time. So I'm just going to look at what's the probability of getting a sum of a 5 and then add that to the probability of getting a sum of 6. So let's go back to the document camera. So let's look at which ways I can get a 5 first. So the probability of getting a sum of 5 or a sum of 6 is equal to the probability of sum of 5 plus the probability of a sum of 6. So can anyone tell me on this left-hand side, where is the first place you get a 5 when you add up the two numbers? 4 and 1. Here. So this is the first one here. What's the next one in the next row? Yep. Then what's the next one in the next row? Yep. And the last one, 1 plus 4. What do those form? A diagonal. So all the ways I can get a 5 lie along this diagonal here. Then I can do the same thing for 6. What's the first way I can get a 6? 5 and a 1, and then 4 and 2, 3 and 3, and then it's just flip them around. So then this diagonal here is the sum of 6, and this is the sum of 5. So how many ways can I get a 5 here? 4. How many total combinations are there? 4 and 36. So there's 36 possible combinations in the sample space and 4 ways I can get a sum of 5. Now, the next one. How many ways are there to get a sum of 6? 1, 2, 3, 4, 5. 5 out of the 36 possible outcomes. So what happens when I add those? What do you get? 9 over 36 or 1/4? Everyone okay with that? What sum has the highest probability? Yeah, and why? It has the longest diagonal. So 6 and 1, 5 and 2, 4 and 3, and then just flip the others. So that's 6 possible outcomes out of 36. So the probability is 1/6. Everyone following? Okay, the next one. Find the probability of getting a sum of 14. Yeah, it is. What's the highest sum you can get? 12, so you can't get a 14. Can't get 14. Can't get a sum of 14 with 2 die rolls, which implies its probability of sum of 14 is equal to 0. So the last one, sum greater than 9. So does it include a sum of 9? No. If it said greater than or equal to, it would. So what are the sums that you can get greater than 9 for 2 die rolls? Yeah, 10, 11, and 12. So you're basically taking the probability of 10, 11, and 12, and you're just adding them. Probability of 10 plus probability of 11 plus the probability of 12. Someone tell me what the probability of 10 is. 3 out of 36. You can get these 3 right here. So that's 3 out of 36. What's the probability of 11? 2 out of 36. You can get a 6 and a 5 or a 5 and a 6. And finally, what's the probability of getting a 12? 1 out of 36, 6 and 6. So 1 out of 36. If I add those together, what do I get? 6 out of 36 or 1/6. So are there any questions over any of that? All right, next time we'll start on section 4.2. If your chapter 4 homework isn't open, I'll open it if you want to start it. It is quite long, fair warning.